today. We're going to define the different types of bearings and talk about where and when you might want to use the different types of bearings. And we're going to talk a little bit about bearing mounting and how you should be mounting your bearing sets. That's typically where I see some errors in the robotics community. That's a lot of times they use the right bearing, but they don't mount it correctly, mostly because of the alignment to the paired up bearing. So what is a bearing and why do we need it? Anybody come up with any reasons why we might need a bearing in an application? Is that great?
So you're not having the metal sliding its
Metal on metal sliding, yep. Any other reasons, Ben?
wheels that slide smoother, or that roll smoother, I guess.
Right, so there's two different kinds of friction that you experience. And bearings combat friction, basically they're a combat friction element. The metal on metal can actually get micro welds if you're trying to slide metal on metal, or metal on metal is rubbing. If you're trying to run a shaft through a hole with no bearing surface in there, you actually get micro welds, and it actually joins one metal to another. And what a bearing will do, it either puts a rolling element in there or it introduces a component of oil which will fill that groove and create a sliding surface with the oil. So we talked a little bit last time about efficiencies of mechanisms and how efficiency will eat into your power. With bearings and with the right bearing sets, you raise the efficiency of the system because you don't have the frictional losses within it. So bearings combat the friction and they help the efficiency of the system. So what different kinds of bearings are there and how are they classified? I've got a couple examples up front here. I'll try to display them here maybe in the light. Can you see that, Paul?
Yeah.
This is what they call a thrust bearing. And basically the loading on this set can only be in line with the shaft. So this is like a typical dial turntable on your Lazy Susan or what have you. This is what they call a thrust bearing. And then just an example here of a radial bearing, where imagine this was being on a shaft, your loading could take place radially on that shaft, and you can load it up that way. You see that in the camera? You guys can come up here and see these afterwards. And I've got another example here, but it's not very clear because it's all encased. So as I was talking about with these bearings, you've got a radial bearing, which takes the load perpendicular to the shaft, and then you've got thrust bearings, which can take axial load on the shaft. And it's important to analyze your subassembly and know ahead of time which types of forces you're going to experience in the subassembly. So that way you can know which type of bearing to pick out. It's not just a matter of going to a drawer and picking a bearing. You got to know a little bit about that bearing and whether or not it can handle radial or thrust forces and how much it can handle when you're doing your designs. So some bearings that can only take thrust, some bearings can only take radial, and then there are some compound bearings that can take both. You've got some deep groove ball bearings that can handle radial and thrust load, and then you've got some other kinds of bearings that just take thrust load. So as I said before, you've got to consider the whole assembly and bearing set. Now when I say a bearing set, usually bearings are used in pairs, and that's because you're best to have a bearing on either side and the loading in the middle. But there are some other systems that you can design, and we'll walk through those a little bit later. I brought this model up here because I know the Raptors were talking a lot about square drive this year. So we're going to kind of do an in-depth analysis on this particular mechanism here and show you what I'm talking about when it comes to thrust and radial loads. So if I look at this first bearing set, and they're kind of hidden because it's a motor, but within this motor there's a bearing on the front and then there's a bearing on the rear, and then there's a loading on the top. The loading is all with this belt system pulling that motor shaft sideways. So that's what they call a radial load. Obviously you don't have a lot of choice when you're picking out a motor, except that you have to upsize the motor or downsize the motor to get different bearing sets in there. Or you can trap the load between two bearings. So for instance, you pull this motor back and you put a bearing top and bearing bottom, trap a shaft in there, and then put your load on that if it was too much for just the motor bearings. So in the second series here, excuse me, you've got a shaft that runs mostly through the assembly. Now, I didn't digest this much, but I'm pretty sure that they're going to have a bearing down here, and this is the shaft that we're talking about here. So you've got all kinds of different loadings on this. You've got radial loadings from these belts being strapped over here, and then you've also got thrust loading due to this bevel gear set that's pushing thrust down here. And then you've got some compound forces when this thing turns around as well. But I don't know if they've got just a bearing here or a bearing here and no bearing in the middle, but if they've got a bearing in the middle, that brings up another issue that we'll talk a little bit later on about how you can, well, you really don't want to have 3 bearings in a row because they're very tough to align. You know, actually eat into your efficiency of your system because your bearings are locking each other up. So over here we look at the next bearing set. You've got a little stub shaft here. It's got the thrust loading from the bevel gear on it this way, as well as the radial loading from another belt system down here. Is there any questions on that? You guys clear on radial and thrust loads? So finally, our last bearing set down here. This is actually pretty nicely designed because it's trapped within one housing. You can align these bearings fairly well with just one drill through. But you've got, again, radial loads here and a hidden thrust load when you're turning this thing on the carpet. You can imagine this wheel wanting to move back and forth. So you're going to have to watch out for some of these hidden loads in that thrust load down there. So there's all kinds of different bearing types. Some of the major ones here are plain bearing, rolling element bearing, jewel bearing, fluid bearing, magnetic bearing, and flexure bearing. Your plain bearing is pretty much the simplest as they can get. It's basically a bushing or a single rolling element against metal on metal or plastic on metal. Basically they are sized with pressure times velocity. So if you look in your design calculation books for your plain bearings, they'll usually give you a PV rating. And what that is it's your pressure times your velocity. And that's how you size a particular bushing or plain bearing. They are really good at a lot of things. Mostly in case where you have a situation where you're not getting a full rotation on a mechanism. For instance, if I'm only doing quarter rotations like this, if this was a radial bearing, that would be a good instance for a plain bearing because the balls are not getting full rotation within their cavity. It would be a bushing, just get brought back and forth. That's where those bushings excel. If you're going really low speed on a full revolution, there's some use for plain bearings. I think the Raptors used a plain bearing on their in-feed systems because there wasn't a lot of load there. If you just want to bush, there's make like a bronze bushing that would call them a plain bearing category. We used some bronze bushings in our extended wheel actuator this year because we did not have a full rotation there and it didn't have a lot of load when it was rotating. Now it had a lot of load when it was locked up, but where you need the bearing is when things are actually trying to move. That's what you want to compensate for. Any questions on plain bearings? Rolling element bearings, these are probably the most common you're going to find out there in the world and in robotics. The two I've got here are ball bearing, which is called out in this upper structure here. And what they call, you've got an outer race on the outside there. You've got the actual rolling ball elements inside of that. Between each rolling ball, you typically have a cage mechanism. You can see in here there's a metal cage binding all the balls together to keep them radially aligned. And then within that, there's an inner race. So when we talk about bearings, you've got outer race, balls, cage, and inner race. It's that same kind of construction down in a roller bearing, and instead of the balls, what you end up with are cylinders, or sometimes needles. They're called roller elements. This type of bearing here can take a lot more load than this can here. heavy industrial applications. And both these sets of bearings come sealed or unsealed, and by that I mean this is an unsealed bearing here where you can actually see the balls and see the cages. When you have an application that's really dirty or has a lot of dirt, you want to keep grease in there or whatever, then they'll actually put a seal on that between the inner race and the outer race, and that seals in the grease or seals out the dirt in many cases. They call that seals. So I don't have seals pictured here, but I do have a sealed bearing up here later if you want to take a look at it. Some of the different ball bearings. There's a deep V and an angled ball, and a lot of those, instead of just the radial load, which is just a normal ball bearing, just takes the radial load typically. You won't find a lot of thrust into the regular ball bearing. They make a deep groove V ball bearing, or deep V ball bearing, and that takes not only radial load, but also thrust load. Sizing these bearings, typically for a machine design application, you would look in a manufacturer's handbook, and you're going to find a load rating for that bearing in their specifications, which you'll find is a static load and a dynamic load. So the static load is any non-moving load force that bearing needs to take. For instance, in a vehicle, you're going to divide the weight of the vehicle by 4, and that will be your static load for your wheel race bearing. In a dynamic situation, you can imagine that wheel hitting a curb. That's more of a dynamic load. It's going to take a high impulse to that load, and that's the dynamic rating that the ball bearing or roller bearing is going to have to take. So we always want to consider that when you're looking at the specifications for ball bearings and roller bearings, and any bearing for that matter. Any questions on rolling element bearings, guys? Ben?
So if you have a bearing, like a ball bearing with 4 balls in the ball bearing in the inner race, or within the inner race, how is that different than a ball bearing with 12 balls in the inner race?
Well, you'll have to look at the specs on the bearings. Typically, the more balls you have in a bearing, they're usually smaller balls. And so you'll find that it distributes the load better, but it can't go as fast because the little balls have to go really fast to go faster, if you can understand that. So you just have to really look at the manufacturer's handbook to figure out how that's rated for the application. They don't necessarily load them or rate them by the number of balls in them, but they are definitely different types of bearings. I mean, there's probably millions of different bearings out there. Every manufacturer has a standard way of doing that. And a lot of them are common. I mean, you can usually cross-reference an SKF bearing with a Timken bearing and that kind of thing, but they really don't rate them or size them by ball bearing size. Typically, it's a construction method or a speed rating that the ball bearing has, because there are maximum RPMs for different sizes of bearings too.
Okay.
All right. Is that how it's what you're asking?
Yeah, more or less.
All right. So some of the other bearings out there, jewel bearings are in watches. You've got a really tiny bearing load, but you need a real friction-free actuation. You can use a jewel. That's basically a hard surface rotating on a hard surface. Fluid bearings are pretty cool. If you get a big load and you spread that over a real flat surface, you can actually support that load with just air or oil coming out of that bearing, and it turns out to be a frictionless surface. So you can take a 2,000-pound chunk of steel and just kind of slide it along this surface, and it would just kind of coast, friction-free, or nearly friction-free. Magnetic bearings, they're used in like a monorail system. If any of you have seen, I think Disney has a monorail where they float a magnetic bearing along a steel track. They're basically opposing gravity and having no other contact there. You call that a magnetic bearing. And then there's an interesting one called a flexure bearing here down in the right corner. That's basically just using the stress strain of the metal itself to help support the load that you want to turn. These are some of the typical bearing mounting situations that you would have. and the advantages or disadvantages for each one. So as I mentioned earlier on in the presentation, one of the best ways to support a radial load is to have a bearing on either side of the shaft where the load is coming in. That is a way to not have that shaft flex and to support that load evenly between the two bearing sets. In this particular arrangement, they've got a roller element bearing and a ball bearing. And the reason for that is they also are predicting an axial load. So you've got an axial load goes through the shaft, enters this bearing through this step in the shaft here, and then through these roller elements out to this axial wall here. So the common things that you see in the robotics world are orientations like this, where you've got a bearing set in the middle, and then you're applying a load out here. And that's okay so long as you've done your homework and can determine that these bearings can support these loads out here. Because the more this load gets further from that bearing, the loads really go up on these bearings. So you really have to watch your calculations when you're looking at these sorts of arrangements to make sure you don't overload your bearing or to make sure you don't get bending in your shaft, which can also bind up your bearings to the middle. And then I threw this one in here quickly to say, okay, a single bearing with a rod coming out of it, who's going to load that up in robotics world and have it work? Not too many people. That's not a good thing to have there. Those want to try to get bearing sets together, and we're going to talk in a little bit of how to get that bearing, that first bearing, aligned with the second bearing, because that's important as well. You can't just drill a hole in one side of a shaft or one side of the assembly and drill a second hole in the back side of the assembly and put two bearings in it and expect it to work. Those things have to be aligned depending on what types of bearings you're using. When you start looking at bearings, there are clearances between the balls and the inner and outer race. And you can feel with some of these, there's not much clearance there. This big one has very, very, very little clearance. So you can imagine by getting two of these bearings together, if they're off center, the shaft is going to want to run transversely or crooked, and that's going to eat up any power you might want to put in here. The bearings themselves are just going to lock right up. There's different degrees to that, but one of the things I've seen in the robotics world a lot, because you guys just aren't aware of how much your shafts are deflecting or how much alignment needs to take place in the bearing sets, you're losing a lot of your power in your motors because the bearings themselves are eating up with friction and binding. So this is kind of re-emphasizing what I just talked about. There's, in each of these bearing sets here and here, there's a certain amount of axial play where they can align to each other. But if depending on the design of the bearing, there's no axial play, then you've got to machine this hole and this hole right directly in alignment. Or you've got to have a way to align those at assembly such that they're in line. Otherwise, if you get those off center from one another, the shaft will end up being like this, and you're going to eat up all your power trying to get those bearings to turn. Or if your radial load is so far out here, initially it might assemble well, but imagine if this shaft wants to bend. It's doing the same thing then. All of a sudden, your shaft is bending and your bearings are going to bind up, and you're going to lose power or not be able to turn the mechanism at all. Any questions on that? No? Okay. So your bearing misalignment will create friction. It will make for difficult assembly because if your bearings are so far out of alignment, you won't get the shaft through one and through the other. I think the Raptors discovered that a little bit on some of the shafts they were trying to put in their assemblies when their system was racking and getting out of alignment. The bearings themselves wouldn't align and you couldn't get your shaft through there. So it'll lock your mechanism up if deflection occurs, and obviously can cause a mechanism failure or at least accelerate wear. And now maybe your outer race is rotating instead of your bearing sets inside there. So how do we prevent some of that from happening? They make, the industrial world makes these cool things called pillow blocks. Up in the right-hand corner, I've got a pillow block shown. And what that is basically a bearing mounted inside of a spherical bearing. So you've got the outer race of this bearing here is spherical. The shaft goes through here, and this thing can have quite a bit of misalignment when it's bolted down. So if you put one of those on one side and one of those on the other and run a shaft between, now you can actually have, depending how far they are, quite a bit of misalignment and still have your bearing systems in alignment. Mostly because it's not the bearing taking up the slop, it's how the bearing is mounted within that housing. So that's a real advantage for some of you guys that are doing robotic design. If you don't have a way to machine in your bearing clearances, and you're thinking that maybe you're just using sheet metal or whatever, those pillow blocks are really advantageous for that. Another way to get those bearings in alignment are to machine them in. If you've got a solid aluminum housing and you know you're going to run a shaft through there and want that supporting the bearings, you can get it to a machine shop and have them put holes in line. So what they usually do is put a through bore in there, and then they'll come in and turn the back side and turn the front side with the same axes of machine, so that way you know everything is in alignment when they do that. Obviously that's a little bit more difficult to do, and usually you can't do it in-house here. You can't do it with a drill, for sure. But it is definitely a way that's done in the machine design field. So another thing I've seen, and I'm going to talk a little bit about this guy again, just because I want to talk about this main axis here. So let's assume right now that there's a bearing here supporting this shaft, and a bearing here supporting this shaft, and a bearing in the middle supporting that shaft. So now with what I just talked about, with all those bearings, you can imagine one side of the bearing and the other side of the bearing using their alignment to get that shaft in one alignment, and then having a third bearing in the middle and trying to keep that in alignment with the other two bearings. It usually doesn't work. And certainly not in a situation where you've got these risers in between this bearing mount and this bearing mount. Because anytime that you put 1, 2, and 3 structures together, there's going to be some misalignment between those structures. This is attempting, I believe, to use these shafts as some sort of alignment to keep this bearing and this bearing somewhat straight on. But at the same time, if there's a third bearing in here, I don't think that'll work. Not very well anyway, unless you're sending those parts out for machining as well. So just keep that in mind. If you've got an assembly like this, where you're trying to put your one bearing surface down here and another bearing surface up here, and you've got all of this assembly working here, these are going to be out of alignment. So make sure you keep that in mind when you're doing your bearing design, that you don't get things out of alignment. So another way you can help some of that in multiple assemblies are using these couplers. So for instance, I imagine I've got a shaft, 2 bearings on it, and a load in the middle. And I've got that all fixed up as an assembly. Now I want to put a motor on that to rotate it. Well, the motor itself has bearings, okay? So now all of a sudden, if I've got this full assembly and another motor bearing, how do I get the motor bearing shaft to align to the shaft that's already there? One way is to hard couple it, okay? But you imagine if that's out of misalignment somehow and you try to hard couple it, you're going to try to move the motor into alignment with the shaft. The other way to do that is to use what they call a shaft coupler, flexible coupler. And what this does, and the reason these are made is because you've got a motor back here that has its bearing set, and you've got a load system up here that has its bearing set, and this will take up some of that misalignment between those two bearing sets. So this will flex in order to keep things moving smoothly and efficiently. Does that make sense? This is another way to do that. It's a rubber element. It's like they call these spider gears almost. There's two hubs here and a hub here, and they go together, but they're mated with this rubber element. That rubber element flexes again. So you've got one bearing system here, another bearing system here, and that rubber element will flex to keep those two bearing systems from locking up. This is another way to do that. It's called a misalignment coupler. A lot of times these are used in pneumatics. And the same thing applies to pneumatics. You've got the cylinder actuating, and that's on one linear bearing. Okay, that's still got a front plane bearing on the shaft, and that's actuating. Your load system may have another bearing set. So there may be some misalignment between the load system and the cylinder. So you use this, which is a misalignment coupler. What that is two plates, because it's just a compression cylinder. The cylinder presses and pulls. So now you've just got two plates. So as that goes down, those slide a little bit between each other to keep the systems from locking up. But it goes back to the same topic. You've got a fixed alignment load system and a fixed alignment actuator system, and you got to keep those from locking up. So you use these misalignment couplers. Any questions on that? Okay. Any questions at all on the bearing sets or bearings in general? No? Okay. So I think we'll jump over to the second half of our talk today about motors and reducers. I'm just going to be going off of a presentation that was done previously for FRC. Let's see. It was given in 2007 by a couple of guys, Team 65 and Team 217. I'm going to work through some of these pretty quick because they're not pertinent, but what they talk about basically is how do you design your drive system. But within here they talk about some of the motor attributes and the gearing which needs to go to that motor. They talk about traction, which is real important with drive systems. I think we'll touch again on some of these in a later topic for this lecture series when we start talking about drive systems. So here they talk about how you calculate the friction coefficient and how do you find how much thrust you're going to get based on friction of the wheel to the surface. Is the wheel material sticky or spongy? It's a pretty good presentation, but what I want to talk about is the motor part of this through here. So when we talk about first motors, there's only so many motors that you can use in an FRC robot. I'll cover those a little bit later. But your power, continuous power, is limited as 40 amps. Mostly because of your breakers are set at 40. You can get a boost out of that, excuse me, but you can't have that boost forever because it'll blow that circuit breaker. So when you're designing your mechanisms, you've got to go through the exercise like we talked about last time with your simple systems and your pulleys to figure out what's the load back at the motor. Okay, so you've got whatever you're trying to do is the load out the end of the actuator or mechanism. You calculate that back through any log arms that you've got, you calculate that back through whatever you've got in your pulley ratios, and that's what the motor's going to see. Now these motors, when we talk about them, are variable. They don't always have a fixed torque to them, and they don't always have a fixed RPM to them. But instead, as you can see here, they've got torque, and this is the performance of the motor through here. So at low speed, you've got high torque. But as your speed increases, your torque drops. And then the slope of that line is different for each motor. So when they talk about 0 speed and high torque, that's typically your stall torque. So when your motor is pushing as hard as it can, but it's not moving. And then we also learned this year what happens to the motor at that point. You're still smokes because it gets too hot. It's a lot of heat. Yeah. Then you also have 0 load and high speed. You just imagine a motor that's sitting in your hand and you put power to it, it spins really fast, right? That's your free speed running motor, but there's no load on it. So you just start putting load on that, then your speed drops off. So the current, which is right here, is the power used by that motor. Now there's a point in these curves. Here they go into a little bit more math on how to determine what the motor constant is. Some of these are defined for you already in the first stuff. You can look those up on cheap Delphi. But what I want to get to here is, well, we can talk about this one here. There's this elusive 40 amp limit here, right? So when we talk about this current here at stall, you're not going to get that full current all the time on that mechanism. You might get an initial boost of that current to start your mechanism moving, but if you try to use all that current to use your mechanism, you're going to end up blowing the breaker again, because your 40 amps is right here. So most of your mechanism design wants to be all the way through here in a continuous fashion, whatever's underneath that 40 amp curve. So he talks about here, can they operate above 40? Yeah, they can, just not very long. So you can boost the motor, get it moving, and then you're going to want to drop that current before it doesn't blow that breaker. Paul, did you want to add anything here? You're more of an electrical guy.
I think one important thing is to know that if you are operating a motor in stall, that 100% of your current times voltage, which is your power in, goes to heat. And so that's why you often get yourselves into trouble at low speeds or stopped, because every ounce of power you're putting into a stalled motor gets directly converted into heat. So it's just something to keep in mind when you're doing low speed applications.
So here they've given you the equations to work out your current, your torque at 40 amps, or sorry, your speed and your torque at 40 amps. There again, a lot of these have already been worked out for you by some of the other teams if you look on Chief Delphi, but it's important to know where that equation came from and why they're doing it, because we're going to talk about your power curve for your motors. So basically, when you start graphing your power, and like Paul would say, down here, you're not getting any power because it's all going to heat. And as you speed that motor up, you're getting more and more power until finally you've got your max power ratio right there. And then as you get faster and faster, the power of that motor is going to drop off. So any motor does not, basically power, the highest point in power is your most efficient motor operation. It's a better way to say that, in my opinion. Now, can you design for this point up here? Probably not, because you've still got to watch that 40 amp current limit, right? Which is running through there. So what they're talking about here is designing those motors for maximum power at 40 amps. So that you can continuously using the highest power that you get out of that motor. And how do you change that power ratio? Who can tell me that? So if I've got a load out here and a motor back here, and I want to do some efficient design of that motor or that mechanism, what do I do to get into the power band? Zach? Gear it, absolutely. Change the ratios. So So that you could get back down into that power band if you're running too fast, or if you're not running it fast enough, you gear it up so it'll run faster. A lot of those motors that the first supplies can do 15,000, 20,000 RPM. Use it until you get the power to it. Use those 40 amps. Gear that thing up. Power is absolute. It determines the torque speed trade-off. So you shouldn't be driving, you gotta make sure that the mechanism can move the load at your stall current. But if you're doing a continuous moving, a lot of your drive systems, for instance, are continuously moving. You want to be designing those so they hit your max power at your fastest speed or close to it, what your maximum speed is. They go into some first motor comparisons here. I don't know if that's going to be useful for this team. Some numbers on the sim motor up here. So Newton meters is your torque. There's your RPM. So the sim is one that's not very fast, but it's a powerful motor. It's a lot more torque, but a lot less RPM. And they go into some multiple motor conversations here, which is pretty advanced if you start talking about that. But what they're saying is you put two sims, like a lot of you guys do now, you put two sims on your driving motors, or two Neos. Obviously you're doubling the motor force there. So they run you through those calculations here. Talked a little bit about torque last time. Obviously, torque is a force times the distance. That's all it is. So in a motor, you're talking about a winding within there that's generating a magnetic force. And that magnetic force is turning against a fixed magnet, usually on the outside. And that's where your torque is coming from. It's that force times the distance. When you start talking about electronics and that, now they're varying that magnetic force, and they're getting that to flux around. And that's what creates the torque of the motor itself. But it's basically a simple system. It's a torque, it's a force, and a distance generated around a shaft. Two bearings on the outside. Torque determines whether or not you get the job done. So if you've got all the great incentives to have a mechanism that continuously moves, but if you don't have enough initial torque to get it moving, your mechanism doesn't work. So you got to have the initial starting torque to get it designed, and then you got to watch your power, or that current, when you're at your full speed to make sure you're not bumping past the 40 amps. So torque gets it done, gets it moving, and then power determines how fast it gets done. Any questions on that? Alright, so there's many different ways to get that ratio tuned in so that you have the power band of where you want it in your motor. We talked a little bit about efficiency last time. We're going to expand on that a little bit now. The chain and belt system, everybody knows what a chain and belt is, correct? Okay. Your efficiency for that, 95 to 98%. And these are per loop. So if you've got a multi-chain system, you actually multiply out your efficiencies. The chain system is limited a little bit in how much reduction or enlargement you can do, just because you got a sprocket on one end and a bigger sprocket on the other, and you got to make sure that you don't get too small a sprocket for that type of chain size, basically. Your spur gears are the same type of thing, almost the same efficiency here. You usually have a little bit more freedom in your spur gear design than you do in the sprocket design, as far as getting that ratio to match up for what you need it for. Dynamically, if you get in the world of servo motors and mechanism designs, you've got to start watching out for inertia matching and that kind of thing. But that's a little bit beyond this topic here, I think. Your bevel gears here, efficiency 90-95%, somewhere in there. There again, you can get some ratios. Your ratio size are much more limited in the bevel gears. You could see as the mechanism we covered before, there was bevel gears and additional gearing outside those bevel gears. So you could take advantage of that. We talked about that before. The way to determine what the gear ratio is count the number of teeth on the bottom gear versus the number of teeth on the top gear. And that's your conversion ratio. Worm drives, you may have ever heard of a worm drive? Yes, no, yes, okay. So a worm drive is a special type of gearbox. Basically, they call it a worm because this guy up here is like a screw almost. And then there's like a screw cut bevel in the inside of this gear here. So when this turns and screws this way, this gear rotates around this way. They're usually pretty high reduction, but you can see they're not very high efficiency. However, you can't backdrive a worm gear. So when you try to turn this, one way or the other, this won't turn because it taper locks up. So that's one of the nice things about a worm gear. If you need a gearbox that will go and stop and go and stop and go and stop, you put a worm gear on it, it won't backdrive. Gravity won't reverse that gear. It takes the motor to drive it one way or the other to move it. There aren't a lot of worm gears in the first packages that they give out. I think the window motor is about the only one I can think of right now. Imagine that window motor drives one way, you can't drive it backwards until you take the motor on it back the other way, reverse the current on the motor. Any questions on a worm gear? Planetary gears, these are very common in the first world. Basically, you've got a fixed outer ring, you've got a moving sun gear, usually spur-driven gear in the middle or motor-driven, and then you've got these planet gears on the outside that end up doing this orbiting fashion about that. And then you can do multiple stacks of these within some of the gearbox ratios. So you take one gear set, put it here, and then another gear set, which is spined off of this guy on the next side, and you can get multiple sets of these. Efficiency, 80-90%, sometimes you get a little bit higher than that. There again, the more gear sets that you stack up, you've got to multiply that efficiency through your system. That's true for just about any multiple gearing ratios that you have. Questions on that? These are kind of cool in the packages that they give first because you can get different gear sets for one gearbox. I don't know, was it Versa? Versa is the one we've got, and you can get anywhere from a 3-to-1 to a 10-to-1 and put in that same gear set, and you can stack up to 3 of those. But you can also get too much power in that too. Spur gears, we talked a little bit about this last time. Here where they're talking about multiplying efficiencies. So you've got gear set number 1 and gear set number 2. So the total efficiency through that is 0.9. It's not 0.95 the whole system, but for each gear set, you've got to multiply that efficiency up. The gear ratio, first gear set, you don't need to count teeth here versus the teeth over here. And the second gear ratio is you count the teeth here versus the teeth over here. There again, gearing is in there so that you can get your mechanism to work. You got to start that load moving, and you want to keep it running at your maximum efficiency or power of that motor. So your you're gonna choose these gear sets so that your mechanism can work with that motor. Here they work through some calculations, basically on a drive system, so they're trying to push this drive wheel with this drive set of gears. And for earlier in this presentation, they showed you how much force you could actually get based on friction and traction to the whatever system they were working with. So what they're trying to do now is match it so that this force, they never know, you could get a lot of force here, but if you don't have the traction to go with it, or the friction, what's going to happen? It's just going to spin, yeah. Like a brake torque out here with a car, it's just going to light up the road. So there's no sense in having that much force or that much torque if you can't apply it to the mechanism that you're wanting to move. In this case, a wheel on a carpet. So here they walk through the base and some of the calculations for each wheel. I'm not going to sit here and walk these through. You guys can read through it if you want. But basically it's what I talked about, where they're applying a torque to a wheel and they're knowing how much force they can get. They go through and calculate their top speed based on what their assumptions are. Figure their gearing to get where they need to be. So these are all the calculations that you can apply to a drive system based on what we just talked about. And then, somebody went through and actually developed a simulation based on those numbers. And what they did is take a time variable every 0.05 seconds, and they calculate all that out dynamically to see, try to predict how that motor's going, or how that system is going to react. So I've actually done some of this on a couple of previous projects of mine in the engineering world, where you actually don't know what you're talking about, and you need to know, for instance, how long it's going to take to get to a speed. But you can, at each second or at each interval, you can approximate, make some calculations to predict where your speeds and forces and torques are going to be, and you can apply that to different motors and see which motor's going to work. So. Here's the results of their simulation. Basically, they're saying the robot velocity, speed of robot versus elapsed time. So it takes, depending on the ratio they're using, or the motors they're using in this case, upwards of a second to achieve full velocity. So if they put different motors on there, they get different performance results. Not only in top speed, but also how long it takes to get to that top speed. Engineering's cool, huh? So there's a couple of things they talk about that I'm going to emphasize here. Reliability, keep it simple. As simple as you can get. Simple is better sometimes over a much more complex system. It's easier to design, it's easier to build, get it up and running sooner, and easier to fix when it breaks. If you get it in the field quicker, then you give your drivers time to drive it, your programmers time to program it, and then your time to fine-tune that if you need to change it. When testing, make sure the weight of the robot is about right. If you had to add some dead weight because you're going to add a mechanism later, make sure you throw that on the robot. That way it's going to act differently with that additional weight than it will be if it doesn't have it. Consider assembly and disassembly when you're doing your mechanism design. Obviously, if you have to put a gear set together and then you put something around it, builds it out further. If you can't get to that gear set to fix it, and you have to take the whole assembly out and the whole sub-assembly apart to get down into that gear set. So try to apply some thought process to how you put these things together, maybe have some access holes, something else to help you repair the things that are in there. Reliable fastening systems, every competition, every match just about, they're pulling fasteners off of that carpeting out there. So make sure things are reliable, best way possible. Clamps are better than set screws. There's a lot of design considerations there. Support shafts appropriately. This is something that I often see go wrong. We talked about that one bearing out there with the shaft coming out of it. That's obviously a little bit exaggerated, but oftentimes you'll see two bearings and then a load way out beyond the bearings. Or sometimes you'll have a bearing and a bearing, and this long skinny shaft with a load in the middle. And this poor shaft is just flexing back and forth, and those bearings are going to eat each other up because the flex of the shaft is kicking those bearings out of alignment. It'd be much better to take one of those loads and move it back over towards the bearing so that you're not deflecting the shaft as much. And of course, reduced friction will improve durability and controllability. So if you get some friction in there, and if it's flexing something, your control system's going to go crazy trying to compensate for it, and you need more consistency in your drive system. A couple of pictures here they had thrown in. Here's a load system that's fully constrained. You got a bearing and a load. So that all looks pretty good. And then you've got a motor attached to it out here. And it's hard to tell what kind of coupling that is. If it's a solid shaft coupling, that could be binding up. That would be a perfect place to use one of those flexible couplings that I talked about, because you've got the motor fixed on one end, and the motor has two bearings in it. In this case, it looks like a reducer or a drill motor. But anyway, this is on its own rotation shaft, and this is on its own rotation shaft. You'll never get those directly in alignment, or very rarely anyway, so you put a flexible coupling in between. This is a picture here of some spur gears. Looks like maybe a drive system. Looks like 3 motors in it. Can't quite see what that's a picture of. It's like some chain drive system. Here again, loads in the middle, bearing on the outside, bearing on the outside. Well-designed system. I'd be curious in this case how they got those two aligned, because it looks like that's an assembly. There again, you gotta consider the fact that these just being bolt heads, there's some clearance in bolt heads, right? So you gotta make sure that if these are changing in any way, that your misalignment of this bearing to this bearing isn't causing trouble. Zach?
Is it still a major problem if you're having the parts like printed by like a laser cutter, or can you trust the laser cutter that it's gonna be accurate enough?
That depends.
Okay.
A lot of times laser cut parts don't come into size. They certainly aren't sized for a pressed-in bearing, but when you start talking about flange bearings, they might be okay. And then you've got to look at, okay, well, my bearing's off a little bit in this laser part. How is that bearing going to get mated to my other bearing, which is out here somewhere? If that's on a piece of sheet metal that's doing this, there's no way those are going to be in alignment, right? So in this case, it looks to me like they've got machined surfaces here and here, so that's going to help keep things in alignment. Whereas if this was just a plain old piece of sheet metal that was bent up, you have a lot more trouble with that. Not sure why they threw this picture in here, this is a cool little chain tensioner. But, in this case, they've got some unsupported shafts here. Now, like I said, this is potentially okay, as long as they've sized the bearings on the backside and got enough distance between the bearing sets to handle any kind of load that this is putting on. But these chain drive segments not only have a static load when you tension the chain, but also when you're kicking that drive system in, that generates a torque, which generates a force, which in turn generates a radial load on that shaft. So that's where you have to consider not only the static loading, but the dynamic loading of your system. Any questions? No? Okay. Just a couple more things to show you. These are the legal motors for last year. Who knows what they're going to have in 2020. But these are all the legal motors. We talked about this guy here, which is a motor reducer combination, and there's that worm drive right there. And the snowblower motor. Looks like another couple more worm drives here maybe. So those are legal motors. Each one has its own pluses and minuses. Here is some of those specifications for those motors. So you can each one has obviously a different component. Max power, stall torque, it's all in Allison's inches here. We talked about your free speed or your running RPM. That's here. So we got some motors up here, 19,300, 18,700. 775s. So there's opportunity here for a lot more RPM than some of you kids are putting in your designs. Now, is there a lot of torque out here? Probably not. Remember that power curve tapers off at the end, right? But there is opportunity. You're not going to get max power at 100 RPM either. So you're going to put a fairly decent reducer on that.